Everyone, and welcome to the latest installment of Coda's webinar series, in which we showcase the experiences, capabilities that are driving the development of world-class decommissioning in the industry sector here in Australia. My name is Sean Sadler. I'm the General Manager here at the Centre of Decommissioning Australia. Today, we're going to be talking about challenges and solutions in well abandonment planning. So I'm really delighted to welcome our special guest, Mr. Chris Wilson, the CEO and Managing Director of Labrador, Australia's first independent well management consultancy. Chris started in the oil and gas industry in 1987, working for Whoppet, originally in their subsurface team, before transitioning to drilling whilst working for Chevron in Papua New Guinea. Chris joined Labrador in 1997 and over a 26-year period has consulted for a wide variety of companies on various drilling roles. Today, Chris is going to tell us a little more about Labrador and then use a case study to highlight how past approaches to well design and management are now posing some interesting challenges when it comes to planning new well abandonments. Don't forget to put your questions in on the chat, but for now, over to you, Chris.
Thank you, Sean. As Sean mentioned, Labrador was one of the first consulting companies, drilling consulting companies in Perth. And has had the pleasure of working for pretty much every operating company in Australia and sometimes a little bit beyond our own shores, not only just providing people, but doing engineering studies on every aspect of the well life cycle, from concept through to decommissioning. And the great thing about that is it's given Labrador an opportunity to take a peek into various different operations, different drilling styles, different well styles, different geological basins, and of course dealing with lots of different challenges that operators face. And what I'm going to be talking about today is one of those challenges around well abandonments and how very quickly what looks like a fairly simple problem can turn into a fairly complex problem. So welcome everybody and thanks for joining us today, and I'll get started. So what I'm going to talk about today is a subsea development well, or a former subsea development well, that has within it, through a workover process, an unretrievable retrievable packer. And therein lies the problem for the operator. They've got a reservoir section with a primary cap rock sitting immediately above it, but they've got an object in the well that's preventing them from gaining access to that cap rock and doing a conventional abandonment. So the problem statement is can we gain access to this well to set abandonment barriers in the primary cap rock? That's the first problem statement. Is there an alternative abandonment option if we can't get to that primary cap rock? And can the well actually be left as it is? Do we actually have to do anything with the well? So these are the three questions that the client had coming into Labrador. So we built a little plan around how we were going to assess this well and the ability to abandon it. And to answer the first two questions about establishing barriers in the primary cap rock, we looked at two options. One was to intervene conventionally and establish barriers. In other words, trying to get through that unretrievable packer. The next option around setting those barriers deeper in the well was to drill an intercept well. And we have two options there. We can drill a brand new well and re-enter the old well below the obstruction, or we can drill a sidetrack from the existing well. Next one was to have an alternative cap rock abandonment, so to look at the options around that, and then to look at what's existing in the well and whether that is sufficient to actually just say, actually the well is fine, we can sever the wellhead and move on. So those were the four scopes. So a little bit of history around this well, and it's the history is important as part of the context for what we're looking at here. So this well was originally drilled, I think, back in 2004, and the original well was an appraisal well looking into the reservoir, and that's this red well here. Now, the first well didn't meet the target reservoir and had to be sidetracked. So there's an original well and a sidetrack. And then once that sidetrack had penetrated the reservoir, there was some cement plugs set with a view to doing a sidetrack. Now, what's important to note here is some of these cement plugs weren't exactly ideal. So you got a reservoir penetration with not quite an ideal abandonment scenario. There was then another well drilled, sidetracked into the reservoir to again appraise a different section of the reservoir. Again, more cement plugs set with a reservoir penetration. And again, top of cement not quite clear. And then they came back later and drilled a new well, which again didn't quite meet the target. So that was abandoned and then sidetracked. And then there was a new horizontal well drilled that found the reservoir, and then they drilled a sidetrack to that. And then there was also a lateral as well. So there's multiple reservoir penetrations in here, but all through this single, what I would call a mother bore, so the original well. And to make matters complicated, these wells all had different names. So when you're looking back through the records, this well name has a different well name to that and a different well name to that. So you've got to kind of link all of these different well names and different bits of information from different generations of drilling and different drilling rigs and tie all this information back together. Now, the reason they've got a problem here is a little bit to do with the history of the well. So the well was brought onto production and produced for about 2 years, after which there was a pressure anomaly. They did a workover and found corrosion in the tubing hanger. So the well was suspended with a deep set plug in the lower completion, and this suspension packer was actually set a lot higher in the well. A dummy hanger was installed, and the well was left with a view to coming back to it later to fix it up. However, annulus pressure was observed, so another workover was performed. This suspension packer was moved to deeper in the well. There was a remedial cement job performed on the 10 3/4 production casing. And then they attempted to retrieve this suspension packer and had a lot of trouble doing so, to the point where they spent a good couple of weeks trying to retrieve the packer. In the end, started milling on top of the packer, which meant it couldn't be fished conventionally. And in the end, they just said, no, that's enough. We need to just set some cement, cut the casing and suspend the well. We'll come back to it later. Well, later never really occurred, and now the field is going through a decommissioning phase. So now this well needs to be decommissioned along with all the other existing production wells. So it poses the challenge of what is the best way to abandon this well. Do we have enough information to leave it as it is? Do we have to get into a deeper barrier? Or can we look for an alternative cap rock with which we can abandon the well? So Labrador started this study in part of those 4 phases. So intervene and establish barriers was the first part of this study that we looked at. And when you draw up the well in a series of schematics, it looks kind of easy to abandon this well. You drill out this first cement plug, you tie back the well and establish a good primary barrier. You then drill out this cement plug, recover and or mill out the packer. So then you've got access to the well. You then recover the deep set plug that was set, and then you have access all the way through to the reservoir, where you can set your primary and secondary barriers. Now that all looks easy when you draw it up in schematics, but when you actually start to work through each step, that's when you start to realise there's problems that can occur. And that's exactly what we did. So we mapped out every one of the steps that we needed to take. And for each step that we took, we assessed all the possible outcomes. So an example of that might be if you're doing a pressure test, the pressure test is either good or it's not good. If you're running a cement bond log, you've either got good cement, poor cement, or no cement. So for every step we took, we mapped it out and built this rather large sort of mind map. And as you can see from some of the colours in here, we have green, which means we've had a successful outcome and we can move to the next step. We've had an amber, which means we could potentially move forward, but there might be issues. Or we end up with steps that are red, which means actually we can't proceed any further with this step. And the good thing about mapping out the operation in this scenario, which does feel like you're going into a very detailed engineering phase very early, is that it helps you understand what is actually feasible to achieve, what sort of contingencies you might need to have in place in order to make sure you achieve a certain outcome, or it drives you down a particular path of abandonment. So you might realise that actually we can't do something, we have to come back and think of another way to abandon the well. So this was a great way for us to assess risk, establish what contingencies would be required, and help build up a cost and time estimate for doing a particular style of abandonment. So this is an example of part of that decision tree breakdown. So fishing the suspension packer which was in there, and it's a conventional suspension packer that we've all used multiple times. So fishing that out, the step is running a milling assembly. So if that's successful, we need to do some clean out runs to make sure we can get to the deeper set plug. And this is the equipment we need to do that. If we are successful, we need to pressure test. So the pressure test is either good, barrier confirmed, move on, or it's bad, we need to find the leak. If we've got a leak, we need to isolate it, and that's potentially leading us down the path of a scab liner, which then leads us down the path of restricted size of tools we can run in the well. So that starts to create some problems. But if we're not successful in milling out that packer, then we probably need to define a timeline. How long are we going to spend doing this? What's economic? What's rational? Do we spend a day doing it? Do we spend a week, 2 weeks? So we need to establish that, and that's a decision point in itself. If we're unsuccessful, we need to establish what is sitting here in the well. What does this cement look like? The reason we need to know that is we've got an option to sidetrack the well and do an intercept to get in deeper. So running a bond log will give us an outcome. We either have good cement, no cement, or partial cement. Now you might think in this instance having good cement is a good outcome, but actually having good cement in this casing size restricts the hole size with which we can sidetrack, which then leads to an outcome later where we can't section mill the 9 5/8 to install a barrier. So what we actually need to find is that we've got bad cement or no cement in there, so we can cut and recover this casing, set a bigger whipstock, and actually sidetrack in the correct hole size. So mapping out all of those scenarios helped us build up a risk profile. It also helped us establish a list of information that we didn't know about the well. So these are things that I like to refer to as unknowns that are often lurking in suspended wells. Now the intercept well option, intercept wells all sound very scary because it's a whole new well. You've got to drill a new well, you've got to range in and find the existing well, which can be quite a time-consuming process. You've then got to gain access to that target well, which can be a challenge in itself. One thing we found throughout the process of this study was that intercept wells are becoming more and more frequently used. So we're able to tap into some fairly recent experience when building up a program for this. So for the intercept well, it's drilling a new well, ranging in and finding the target well. And once we've done that, we position ourselves so that we're adjacent to the target well. So this here is the 8.5 inch hole from the intercept well, the new well. And what we have here, the red lines represent the 9 5/8 casing, and the green line represents the 5.5 inch tubing, which is sitting on the low side of the casing. And the angle of the well on the screen there is the actual angle of the well bore at the point of intercept. So once we've found the well, we then go in with a milling assembly and we mill a window into the target well. So we actually chew up the 9 5/8 inch casing and we start to mill up the 5.5 inch tubing to enable us to gain access lower in the well. So we're milling a window in here. Now, in this particular instance, that sounds fairly straightforward to do for people that are experienced in milling windows. However, what we end up with is what we call a patio of this 5.5 inch tubing. That's about 2 metres long. And as we know, gravity wins every time. So that patio is going to want to lean down and cause a restriction every time we run in and out of this hole. Also, on the other side of the mill, we've got 5.5 inch tubing sitting loose in the well. Ideally, gravity winning, that tubing sitting on the low side, and we can build our window such that we're entering the well on the low side and we've got the best opportunity to gain access. But that's not without risk. So once we've milled our window, we've got access, we can then run into the well with at least 2 inch coil tubing, gain access to the well, gather some data. But then we've still got to solve some challenges further down in the well. We may need to section mill 9 5/8 inch casing, but we've got 5.5 inch tubing in there. So whilst this seems like a sensible approach to get deeper, again, we run into more and more problems as we get deeper into the well. But it is an option to gain access deeper into the well and one that's worth exploring. Apologies for the crude looking diagram here, but this is the sidetrack option for doing an intercept well. So we've already got half a well drilled already. So we can set a whipstock, sidetrack our way around, range in, find the bottom of the well, gain access, just like I described before, and set our primary and secondary barriers. Now, earlier on in my discussion, I did mention that working out what cement was in the 10 3/4 by 13 3/8 annulus was quite important. So this is the decision tree that we came up with. So once we do our bond log and establish what's in the 10 3/4 by 13 3/8 annulus, we either have good cement, bad cement, or no cement. But then we need to look at the next annulus beyond that, which is 13 3/8 by 17.5 inch. We either have good cement, bad cement, or no cement. So we have this range of scenarios that could possibly play out whilst trying to sidetrack this well and do an intercept deeper down. So what this points out to us is another series of unknowns that lie within this well, that had we had more information up front, we might have answers to these questions and would make these decisions a lot more straightforward. Now, the alternative caprock option, this is quite interesting. So there is an alternative caprock in and around the 13 3/8 shoe. When this well was drilled, it actually penetrated the reservoir in 12 1/4 inch hole. This casing shoe is good for reservoir pressure, has a really good leak off. So we have this alternative caprock sitting up a bit higher. So that's good news, means that we might not necessarily have to gain access deeper in the well. However, we still have a series of unknowns that we have to solve for before we can make that decision that yes, this is a viable option. So again, it comes down to running a cement evaluation log. We need to establish, do we have good cement in this annulus and what's the height of that cement? And we need to know what's the cement like in the 13 3/8 annulus as well. Making sure we've got good cement across both of those annuli so that we can put a cement barrier that provides rock to rock through the well into a suitable caprock. So again, another decision tree, do we have sufficient cement? Yes or no. If there's no cement, we can actually cut and recover the 10 3/4 casing and then set our cement plug in the 13 3/8 casing. Or if we've got no cement or poor cement in there, we have to look at perf wash cement scenarios or even milling casing, which again starts to get very expensive and not a desirable outcome. And then comes the question of, well, can we actually leave the well as it is? And that's almost a question a little bit too hard to answer because we have so many unknowns that we need to resolve first. We don't really know how good the cement is in this annulus here. We're fairly confident on the annulus cement here, although we don't have a bond log. We do know where it is. So it's about reaching an alert position, as low as reasonably practical position with your barriers, knowing where they are and the information you've got. So there are a lot of unknowns to actually say whether you could or could not leave the well as it is, and that would require a considerable amount of more work risk assessing each one of those cement jobs. So what have we learnt, or what have I learnt throughout this process? Well, there's a lot of the devil's in the details. Those of you that know me know that I refer to well abandonments as like renovating a house. It all looks good on paper until you start tearing plaster off walls or pulling walls down, and then the truth is staring you in the face, and that's the same for well abandonments. So what appears to be simple can turn very complex very quickly. And by taking each one of those steps and analysing them in a bit more detail of what the potential outcomes are, you can understand just how complex things can become. Resolving the unknowns in a well can cost a lot of money when you've got a rig sitting there waiting, ready to go. So if you've got a well where you don't know where the top of cement is, you've got to run a log or do some sort of investigation to find that. It's often better to try and do that prior to the rig arriving on location if you can. Even better if you can do that during the construction phase or any workovers. That can allow you to remove some of those unknowns. So reducing or solving those will save you a lot of money during your decommissioning period. One thing I would say to anybody drilling a new well is avoid leaving any unknowns for the future. So don't just pass them off as an expense later. Try and solve as many unknowns as you can during the construction phase. If you're suspending a well, think about the final abandonment. I've got a habit of teaching young engineers to start with the end in mind. But as I've come along and done a lot more abandonment work, we actually have to keep abandonment in front of mind all the time. During well construction, we need to be thinking about it. If there's any changes in well design, we need to be rethinking about well abandonments. If you're going in to do a workover or suspend a well, think about the abandonment phase. What information can I get now, or what can I do now that will make that abandonment a lot simpler? Don't leave unknowns on the table because they will cost you a lot of money and they do leave you exposed to risk. Final lesson that I've learned is intercept wells are actually quite common now. They're almost an everyday occurrence in the US, in particular in California and in parts of Colorado. They're drilling intercept wells for abandonments all the time. In fact, recently the company that we partnered with on this study was able to successfully intercept, re-enter and abandon a well that was over 90 years old. And that included milling a window in the casing and gaining access to the lower portion of the well. There are new tools available for ranging, which make it a lot quicker and a lot better and more accurate than what it has been in the past. And this is technology that's taken from drilling relief wells for blowouts and applying that technology to abandoning wells. So a couple of the images there now, these companies have the ability to mill exactly what the window is going to look like. So to optimize your intercept position and allow you to intercept appropriately and mill a window that allows you to gain access to the tubing and not get stuck in the annulus, all of that kind of stuff is now available. So that's some of the new technology that's out there that can now be put to good use. And now it's time for questions. Over to you, Sean.
All right, thanks very much indeed, Chris. Some really, really interesting stuff there, some really great context. People online, encourage you to get some questions in on the chat or Q&A sections in Teams there. Chris, one question I had initially, with such a complex history to the well, did you find that there was robust and well-curated information set available to you, or were there gaps?
There were certainly gaps, but the more we dug, the more we got, which was good. But where some of the gaps, some of the biggest gaps occurred, I think, is people keep a lot of information in emails and don't necessarily transfer that to a central data repository, SharePoint, Teams, or a file server. So that's where a lot of information does get missed. So yeah, luckily people were able to drag up some emails and help us out with some more information. But yeah, there was some gaps for sure.
Yeah. And you did speak to it a little bit at the end there, but I was taken aback a bit initially when you started talking about intercept wells, and you talked a little bit about it at the end of the increased ability to sort of range around these wells. Is there anything you can specifically point to in terms of the nature of the tools and the operation of the tools specifically that's increased levels of comfort with doing that? Because back in the dim distant past when I was designing wells, that would not have been my first go-to solution.
Yes, so some of the new technology there is around actually ranging whilst drilling. So this is fairly new technology that's definitely being refined as we speak. So that's probably one of the best options out there now. If you're not running wireline ranging runs, every 30 metres, and it can actually range whilst you're drilling, it really reduces your cost and time to drill an intercept well.
Yeah. All right, still looking for questions on the chat. If anybody's got anything, just throw it in there. Do you use any sort of platform specifically for your decision tree work, Chris? Or is there some sort of application that you use that you would recommend or talk about?
The software I use is MindJet mind mapping software. So I just use that to sort of map out map out the process, which were some of the examples I showed on screen. There's probably better decision analysis tools out there, but that works for me.
Very good. We've got a question come in on the alternative caprock option. Was the engineering basis of getting this over the line purely related to the ability for the shallower formations to withstand a column of gas back from the reservoir, or are there other factors which need to be addressed?
Yeah, there are other factors that need to be addressed. You need to make sure that in that path from the reservoir to the alternative caprock, there's nowhere else for the hydrocarbons to go. So you're not going to get any cross flow anywhere. So yeah, that's part of that analysis.
And another question that came in was with regards again to the decision tree, how much risk assessment and mitigation was applied? A bit more general question.
Yeah, a bit more general. So for each one of the outcomes, we did put that into a risk assessment, and it was the client's risk assessment process we went through, so so that they could map that through to a larger risk assessment. For us, it was more about identifying the risks, capturing those, looking at the cost of mitigation, any safety risks or anything like that associated with that. So that's pretty much the level we went to. For context, this was meant to be a high-level study, but in order to get the truth out, we had to go into that level of detail. So that was quite helpful. So you almost got to do the reverse of what you do in a well planning process. You've got to do the details first for well abandonments. I hope that answers the question.
We've just had another one in that says, has this well actually been abandoned yet? It would be interesting to plot the actual operations against the risk decision tree in a future webinar.
I don't believe it has been abandoned yet. Yeah, I'm curious about that too.
Yeah, it'd be interesting to see what actually happens in this and compare it to the planning process. It remains simply for me to say thank you very much indeed, Chris Wilson. Really appreciate the perspectives that you've shared today. Thank you to everybody who joined, and particularly to those who asked questions. Hopefully you found it informative, and we look forward to bringing you further examples of this from the CODA perspective. Thank you very much indeed.
Thanks, Sean. Thanks, everyone.